All right, so we're going to start taking a look at 8.1 on this fun, exciting e-learning day. So we're going to be looking at some problems that you guys have seen before, but we're going to start adding some other things to it. So I wanted to make sure that everybody had a really good understanding of what we were talking about when we start talking about some of these problems. So we're going to start with a more simplified problem that says, suppose you are traveling along a straight highway and your position relative to a reference point or the origin is s of t. Now, we know that this s of t, this is my position function. And in a scenario like this, in which b is greater than a, if I was looking to calculate my displacement, well, that means that I'm traveling in the positive direction, or to the right, and that's then telling me that my displacement, which would be s of b minus s of a, is greater than 0. Now, if, say I knew that b was less than a, well, when I go to find my displacement, in this situation, if I'm traveling from A to B, well, this time around, if I'm traveling from A to B, now I'm going to the left, and then that is telling me that I'm moving in a negative direction. I'm moving left. My velocity would be negative, and then I would know that s of b And so this is the really simplified version of when we are looking for displacement and the directions involved. Now, we can say that displacement is the net change in position between t equals a and t equals b. And that's what that looks like when we're traveling along a straight highway. But it's not often that we're going to be just looking at situations like this. So one of the things that I want you guys to see is that, yes, when you guys are looking for displacement, it is your s of b minus your s of a. But that is also represented as your integral from a to b when we have the velocity that we have represented here. So if this is my velocity curve, and I was looking for my net change in position, well, I'm paying attention to my signs. I know that this area is positive, and I know that this area, go away, Joey. Go away, Joey. So much for trying to get a good video in for you all. So my positive area, and then this is my negative area, but I'm just looking for that net change. So I'm okay with my signed areas. And so when we're looking for our displacement, we're looking for the velocity between A and B. Now, our displacement is telling us that these are, in fact, equal. This is what we need to know. Now, when it comes to us looking at the difference between the displacement and our distance traveled, when we're talking about the distance traveled, we don't care what direction you're going. It's just as long as you're traveling, it's counting as a distance. So when we're looking at our distance traveled, we want to use the speed, the magnitude of the velocity, because that's what's going to tell us what our actual traveling is going to be, regardless of that direction. And so when we start looking for our total distance traveled, well, this is then when we start taking a look at the absolute value of v of t. And so if this was v of t, this would be a sketch of the graph of the absolute value of v of t. That brings the area under the curve above the x-axis, thus making it all positive. So when we're looking to calculate the total distance traveled, this is when we take the absolute value of v of t, which is our speed. So these two facts are important. And you've seen these before, but I wanted to make sure that you guys had an understanding of what the difference between displacement and the two equivalent forms, you guys could see that, and the difference between the displacement and your distance traveled is, and how we can calculate those. Okay, so now we have this scenario in which we have a police officer, and she leaves her station on a north-south freeway at 9 a.m. She travels north for 40 miles between 9 a.m. and 10 a.m. And then from 10 a.m. to 11 a.m., she travels south to a point 20 miles south of the station. So here we go. We have our police officer here. She's a motorbike police officer. So she's starting at the police station, and she is traveling north between 9 a.m. and 10 a.m. for 40 miles. So we have gone from our police station north 40 miles. Then at 10 a.m., she turns around, and now she's going to travel south. And as she's traveling south, she's going to go 20 miles south of the station. So now we're going to go 20 miles south of the station. Well, if this is where my station is, she is now 20 miles south of the station. So if we were asked to find the total distance traveled, well, we know she went 40 north, then she turned around. She had to go 40 south to get back to the station, back where she returned, or she started, and then another 20 miles. So in this situation, she traveled 40 plus 40 plus 20, which is going to give us a total of 100 miles. But that doesn't mean that she's 100 miles from the police station. That 100 was just the total distance she was on her bike. Now, if we're looking for our displacement is the difference between where she started and where she ended. So she started at the police station, but then she would have ended 20 miles south of the station. And because it's south, her displacement is negative 20 miles. So I hope this kind of helps you guys really see the difference between your distance and your displacement. We're going to look at a more complicated problem now. Okay, so let's take a look at another example. So in this example, we have a jogger who is running along a straight line with its velocity measured in miles an hour, and the velocity is given by this function for the time intervals of 0 to 3 hours. So this first question is asking us to determine when the jogger moves in a positive direction and when she moves in a negative direction. And so in order for us to figure this out, we need to know when our velocity is positive and when our velocity is negative. So if we're going to sketch the graph of this, the first thing that we're going to want to find out is we're going to want to find out where my zeros are. So if I set my velocity function equal to 0 and I solve for t, I can divide everything by 2, and then I'm left with so I get 0 equals t minus 3 and t minus 1. So we know our velocity equals 0 when t equals 3 and 1. So now if I was going to take a look at what the graph of this would look like. Well, I know that I'm dealing with an interval from 0 to 3. It's quadratic. My y-intercept is 6, and then I have 0s at 1 and 3. And so, knowing what I know about quadratic functions, I know that my graph is going to look something like this. Now, the question says, determine when the jogger moves in a positive direction and when she moves in a negative direction. Well, she's going to move in a positive direction when v of t is greater than 0, and it's greater than 0 on our interval from 0 to 1. So that's for our positive direction. And then our velocity is less than 0 and that's where it's going to be on a negative direction. Now, when we then start to take a look at when it's asking us to find the displacement of the jogger on the time interval 0 to 3. So if I'm looking for my displacement, well, there's a few things that we can kind of look at here. Now, when we're looking for displacement, we're looking for all those little tiny little rectangles that have been added up when we're looking at our velocity regarding the time. And so we said before that our displacement was going to be the integral from a to b, and in this case it's going to be from 0 to 3 of my velocity function, which is 2t squared minus 8t plus 6 dt. So if we're looking for the displacement of this, I have my function. And displacement, well, signs matter, so we're looking for signed area. So all I have to do is find this integral. So when I look for my antiderivative of this, we end up with 2/3 t to the third minus, it would be 8t squared over 2, so minus 4t squared plus 6 from 0 to 3. Now, from there then, I can go ahead and apply that fundamental theorem. Well, that should have a t with it. Okay, so we end up with 2/3 times 3 cubed minus 4 times 3 squared plus 6 times 3 minus, if I plugged in 0 to all those, it's just going to be 0. So we end up with 2/3 of 27 minus 4 times 9, which is 36, plus 18. Well, 3 goes into 27 9 times. So I end up with 18 minus 36 plus 18. So my displacement ends up giving me 0. So what does that mean in the context of this problem? Well, in this case, it means after 3 hours, the jogger returns to where she started. Now, does that mean she didn't move at all? Or displacement is 0? Does that mean that she didn't travel anywhere? Well, no. You can still run around a track and have a displacement of 0, but have run 1/4 of a mile. So the total distance traveled over this interval. Well, when we're looking for total distance, this time we don't care whether it was going to be in the positive direction or in a negative direction. So we're going to be looking at the absolute value. So let me find a pen. So this time around, when we go to find this, now we're going to be looking at the integral from 0 to 3 of the absolute value of v of t dt. But we already know that we've got to be concerned about the signs. So I know, though, from 0 to 1 that that is going to be a positive. So I'm going to be looking for the integral from 0 to 1 of v of t dt. And then I know that this integral is going to end up being negative, but I need it to become positive. So I'm going to go ahead and I'm going to subtract it, because if you subtract a negative, it becomes positive, of the integral from 1 to 3 of v of t dt. Now, we've already come up with our antiderivative. And so for this first one, when I go ahead and I go look for this, well, I know I'm going to end up subtracting 0. So I'm really just looking for my antiderivative when t is 1. So that ends up giving me 2/3 times 1 cubed minus 4 times 1 squared plus 6 times 1. So ultimately, I'm left with 2/3 minus 4, which is 12/3, plus 6, which is 18/3. And so from 0 to 1, I know that this is going to end up giving me 2 minus 12, negative 10, plus 18 is going to give me 8/3. So up here, 8/3. Well, now when I go to look for this one, I got to do a little more work this time around. But I've already plugged in 3 to this antiderivative, and we came up with the fact that that was 0. So this time around, I'm going to have minus 0 minus, well, I'm plugging in 1 again. So that's going to end up giving me the antiderivative evaluated when t equals 1 is still going to give me 8/3. So we ultimately end up with a positive 8/3 because I'm subtracting a negative. And so even if I know that that was a negative 8/3 there, well, I'm looking for the total distance. So I would take the absolute value of that, and we are left with 16/3. So she traveled 5 1/3 miles. Motion problems. So in this problem, we are looking at the velocity of a particle moving along the horizontal axis from 0 to 5. And so we're given our velocity function here. And the question is telling us to use our calculators to sketch this. Now, I'm going to go ahead. I've already actually put it in my calculator. So I'm a step ahead, but feel free to pause this as I go through it and you guys can get caught up. So as I go through this problem, I already know kind of what I'm looking at here. Now, my domain is from 0 to 5, and when I did my window, this is what my window is going to end up looking like. Again, feel free to pause it. So this is what our graph ends up looking like. So I know that I'm going to have a 0 somewhere between 1 and 2, and here we go. There's my rough sketch of what we're taking a look at. Now, again, this is the graph of our velocity function. And so this question for B is, what is its initial velocity? Well, our initial velocity is when we have V of 0, when T is 0. So now I'm actually going to go ahead and I'm going to take a look at my table. Well, when T was 0, we ended up with -8. And so my initial velocity is -8 centimeters a second. And so that's where we're starting. Now, the next part, though, asks us to describe the motion of the particle from 0 to 5. Well, is its initial velocity and it's traveling left because our velocity is negative, and then it stops at some value. Well, if we go back to our graph, we know that it's stopping when our velocity is 0. So I'm going to go ahead and I'm just going to verify second calc 2 what my 0 is. It's less than 1.5 and more than 1. And so my 0 is approximately 1.25. So it stops at T equals 1.25. So this is the 1.25. And then it's moving right because my velocity is positive now, so it's moving right from that 1.25 until we get to the 5. And but let's find out what the velocity is when T is 5. So again, I can go back to my table and so look for when T is 5. So it looks like I have 24.778 centimeters a second. So this is all stuff we did in some of the previous examples, but it's this next one that is going to end up being slightly different. So in this next problem, we're going to be dealing with position, but we're dealing with position when we're given the velocity. Now, this problem tells us that our initial position of the particle is S of 0 equals 9, and it's asking us what is the position at T equals 1 or at T equals 5. So one of the things that you guys are going to want to know is that if you guys are looking for the position, so say I have S of T, I'm trying to find S of T, and I'm starting with my velocity function. Well, what you guys are going to end up doing is s of 0 plus your displacement from 0 to t of v of t dt. Oh, wait, we're going to make that. It's having variable issues. Okay, v of x dx. And so this is our initial condition. And then if you recall, this is actually our displacement. From 0 to t. So when we go to do these, the first thing that I'm going to be looking for is I'm going to be looking to find the position when t equals 1. Well, when t equals 1, we're going to have s of 1 equals s of 0 plus my integral from 0 to one. Now, if I'm looking for my integral from 0 to 1 of this function, we would end up having to do a little bit of u substitution here, but I'm going to erase that for you guys. All right, so now t squared minus 8 over t plus 1 squared dt. So I can go ahead and I can rewrite this as the integral from 0 to 1, and then I can do of the t squared dt minus the integral from 8 over u squared. And so let's let u equal t plus 1. My inner function du is going to equal 1 dt. So when we go to do this, then we know that we're going to end up with the integral from 0 to 1. And our antiderivative is going to be 8u to the negative 1, but it's going to be negative. So minus negative 8u to the negative 1. So I'm left with plus 8 plus t plus 1 from 0 to 1. And then over here I have 1/3 t to the cube, t to the cube, t cubed from 0, 1. And we can go ahead and we can calculate those. Now, if I plugged in 1 here, we end up with just 1/3. It would end up being 0, so I'd end up subtracting 0. Plus so what this is telling us is that we are starting at our initial position of 9, but then we are moving. This was negative, so that's telling us that we're moving to the left. And so that our new position then is if I'm starting at 9 and I'm moving to the left 11 thirds. I think we're dealing with centimeters, right? Let's see if I'm even on the page now. Yeah, so then we're going to end up dealing with a new position of 16 thirds, because that would be 27 thirds. So S of 1 equals this. Now, if you guys were looking to find your total distance traveled, well, then we would end up having to figure out the total distance traveled from 0 to 5 of the absolute value of v of t dt. And so then we're dealing with the same thing again. So we're dealing with and hopefully you guys at this point know how to find that in your calculator. So the approximate total distance traveled would have been 42.587 centimeters. So in this problem, this is the big takeaway for y'all, that you need to know that one.